Well, today we're going to talk about some examples for Newton's law. Okay, so first example, let's say if we have an object and there's a force that's applied on it. And let's say this is 30 degrees, and that's equal to, say, 10 Newton. And there is friction here. We don't know how much, but we know the mu k, which is equal to 0.1. And the m is given. M is equal to 1 kilogram. Okay, so now for this question, we are looking for what is the acceleration? What's the acceleration? So A, we're looking for the acceleration for this object, right, of m under this force. Okay, can we find that? Okay, of the m, right? So this is the object. Okay, so let's give it a try. Changing color here. All right, so I'm going to do a free body diagram for this object, right? So free body diagram is to isolate, right? To isolate the system, right? Isolate the object. So we have mg, as you can tell. We also have an n, right? And we're going to call that n, right? And we also have this f, which has an angle. This one here, 30 degrees, okay? And then we have a friction right there. Okay. So in the y direction, so we're going to name the axis, right? It's going to have say this is y direction and this is x direction. Okay. So why do you pick this x and y, right? I mean, obviously there's a little experience, right? Okay. So in the y direction, we're going to apply the Newton's second law. Newton's second law. So students often forget to mention what law are they applying, right? So in the y direction, so we're going to say summation, right? Summation. Actually, we're going to apply first law, right? First law in the y direction, because we expect that this object is now moving up, okay? We expect that. So summation in the y direction, right? For all the f, right? So we're gonna, this f is not the same as the f, right? So we add them together, we're going to call that the net force, right, in the y direction should be 0, okay? So we assume this object is not like accelerating upward, okay? All right, so let's say, you know, this is true and see what happened. So we have n, right, plus f, this one here, right? So this is the f sine 30, right? So f times sine 30, which is 1/2, right, is equal to mg. So that's the equation you have, right? So from there, we can plug in some value, right? So this is 10, so that's 5 there. And this is 1, so that's 10 right there. So you can find the n, right? So n is equal to 5 Newton. And be careful, look at that. The normal force is not equal to mg, right? So the n is not equal to mg, right? mg in this case is equal to 10 Newton. And the normal force is equal to 5 Newton, right? Equal to 5 Newton. So there are two kinds of n. This is n for normal force, this n is for Newton, right? So they're not the same, okay? So they're not always the same. N and mg may not be the same, okay? Acceleration. So acceleration, this is in the x direction, right? So let's take a look, okay? I'm going to change the color again. All right, so in the x direction, look in this free body diagram, right? This free body diagram, look at the f, right? So in the x direction, we're going to apply Newton's second law now, because we know it's probably going to accelerate, right? Let's take a look. Newton's second law. Okay, so we have the net force in the x direction. So we have f cosine theta, right? So this one here, it's f cosine 30 degree. And this guy here, it's 0.866, right? Okay. And f is 10, right? So that's come out to be 8.7 Newton, right? And how about f, right? So f, I'm just going to write it here and squeeze right there. F, which is the kinetic friction, right? So kinetic friction, put a little k there, kinetic. It's equal to mu, right? And mu k is right there. So mu k, because it's moving, we expect it to be moving, times the Newton, right? And it's an equal sign, okay? Because it's a kinetic friction. So that's equal to 0.1 times the n is 5, right? 5 Newton. So it's 0.5 Newton, okay? So the friction is going to be constant, and it's going to the left. So summation f is going to be equal to this one here, f cosine 30 degree, so which is 8.7, right? Minus this friction going to the left, which is 0.5. And that's equal to 8.2, right? And that's equal to ma, right? And m is your 1 kilogram, right? So a is equal to, right, your net divided by m, which is 8.2, right? 8.2 divided by 1. So that's equal to 8.2, right? So it's pretty big. It's not 10, which is the gravitational acceleration, but it's going to accelerate, okay? So if you have a mu k equal to 0.1, it's not too much, right? So the friction is not going to be that much. Plus that we have this angle here, which reduces the n. So then the n is smaller, so friction is going to become smaller, right? So I like to do a little analysis, right? So students sometimes is wondering, how come I don't know how to write, the analysis, right? So the analysis that we have here, right, that I would say is that the object, right, the M object receive a significant acceleration in x direction since mu equal to 0.1 is kind of small. And the applied force, F, angle, right, is reducing the magnitude of the normal force, right? Of the normal force. Right? So mu is small and n is also being reduced. So then this is why that you can actually see that this A is pretty significant, right? Because 8.2, right? Equal to 8.2. Right? On the other hand, if you actually apply this force, let's say going right this way, then you're going to see this F is still equal to 10 Newton. And then you have this one here, right? This friction. Now you can compute the friction. So the friction here, in this case, it's going to be mu times n, which is 0.1, assume the 0.1 didn't change. And n is equal to mg, right? So mg is equal to 10, so it's going to be equal to 1, right? So then in this case, you can see the net force summation, whoa. Well, you can see that right here. Summation F is going to be 10 minus 1. So it's actually 9 Newton, right? So 9 Newton, so let's take a look. 9 Newton, and summation F is equal to ma, right? And m is equal to 1, and then a. So this is equal to 9, right? So then a, actually in this case, it's 9 meters per second squared, okay? So it's not actually smaller, interesting, right? Because your mu is small and your summation F, because all the F is used to accelerate now, right? Compared to the previous case that some of the F is being applied upward, okay? But interesting, all right? So I'm gonna stop right here, all right? So see you next time. Bye-bye.